Hello. Okay, today I'll be talking just the guidance how to do fault current studies. Okay, so this is the typical book which details about past studies or analysis. So if we go to page 405, it just takes you to the symmetrical fault studies. So this is chapter 10, and this is especially dealt with the three-phase system when the three-phase system symmetry is the same, or we call it balanced faults. Okay, so so basically this kind of fault happens when all three lines are faulted. If we look at on the symmetrical fault examples, I'll be taking you through some of the transmission line or any line that is fed from two generators, G1, G2, and T1, T2, two transformers, and two bus bars, main bus bar 1, and bus 2. Okay, if we assume that we have this kind of parameters of the plant or the equipment item, we can calculate. So the first question, for example, is we can calculate or we can draw the equivalent one-line diagram using the base value of 100 MVA. To do this one, we can use the formula to find the new impedance, Z new per unit, equals to Z per unit all times S new base divided by S old base times V old over V new, or the voltage square. Okay. Based on this formula, we calculate, for example, the G1 parameter, obviously, because we have now a new MVA, 100 MVA, based on compared to 200 MVA, which is an old value. What does this old mean? The actual the network data. Okay, so we just convert into a new MVA, and then once we calculate this one, and then we also calculate T1 as well, transform 1, G2, and T2. And then we also need to convert the line 1 or transmission line into per unit, as normally it's given in ohm per kilometer, which the line between bus 1 to bus 2 is 20 kilometer. So we need to consider this one. So to achieve this one, what we do first is just Z base plus V base divided by S base square, V base square divided by S base. So just the voltage line is 130 kV. And then so now we have a base impedance of 174. Since we have in kilometer, we just multiply by the actual parameter by 20 kilometer, divided by the base, so that we will have 0.5 ohm times 20, which is 10 ohm, divided by the base impedance, which will be 0.057 per unit. Okay, so everything is calculated now. What we do is now we just throw the single line diagram, equivalent single line diagram, so that we just plug this one, all the value, G1, T1 transmission, or the line T2, G2. What we do on this one is, since this is a three-phase fault or symmetrical fault, we just use we only consider the positive sequence component, meaning that we have to put 1 per unit of voltage, which is also we have an equivalent network. So, and the next question is calculate the fault current in amps, which flows when the balanced three-phase fault occurs at bus 1. So what we're thinking is when there is a fault at bus 1, just calculate the fault current contribution. Okay. So here is when bus 1 is faulted, calculate the fault current contribution, meaning that we have contribution from G1 to the fault point, and then of course we could have a contribution from G2. So the step what we do is just ground the generator both in, and then we can look at from the fault point. And then if we look at from this fault point, then what we can do is the two impedance values are in series. So we add this one and then the 3 contribution from G2, we just add them so we can have equivalent impedance. And then since this is shunted, we can connect this one so that this 2 will be in parallel circuit. Then we can just use it as in parallel product divided by their sum, so that we'll have this value. And then from that, we can calculate the fault current, which is IF is equals to V Thevenin, or this is given here, V Thevenin divided by the total Z Thevenin. So that the total fault current in period is 12.286 period. This means the fault current in kiloamp or in amp is 12.28 times the nominal current flow. So because we don't know the nominal current flow, we have to calculate it. So base current or the nominal current is S base divided by 3 times voltage base, which is 100 MVA, the new SEA. S base divided by 3 times 132 kV, so that the nominal current is 437. So the faulted current in amp is this times this one, the period times the nominal current, which is 5,374 or 5.3 kiloamp. We can also calculate the individual contribution of these 2 generators from here to the fault point, and then from here to the fault point, because we know the total fault current at the bus 1. So since we know this one, so what we can do is fault current from G1, the total fault current times Z, or the impedance from G1 contribution, which is all this one, or 0.43, divided by the impedance of from now on plus this one. So that we'll get 10% or 84%, 81.4%, and then the rest is from the G2. So this contribute is 84%, which is the G1, and then the G2 contributes 18%, because you can see that there is 3 components of impedances, and then this is only 2. The higher the impedance, the fault current will reduce substantially. Okay, so this is the symmetrical fault. And now if we compare to unsymmetrical fault current, so that is when we have a generator, transformer, transmission line with some earthing on the start point of the transformer. So what we need to do is, we need to do similarly, however, we need to we need to calculate positive, negative, and zero sequence, because we studied differently. Okay, so what we do is draw the equivalent circuit diagram, and then, well, we can calculate subtransient fault current, and then eventually we can find it phase to ground fault, basically. So if you look at on this one, for example, phase A is 0 kilovolt, because during the fault, the fault current is getting high and the voltage is 0, but the phase B and phase C are unaffected, which are still 12.8 kilovolt each. Okay, so this step is for unsymmetrical fault. Okay, so if for example we wanted to do some further studies for to be face to ground or face to face, sorry, face to ground faults and stuff, we can just go to chapter 11 of this book, the power system book. Power system book. Okay, thank you very much.